Hi everyone, this is third video. We're going to look at slightly complicated examples of plotting using or plotting in polar coordinates. The first one is r equals 2 sine theta. So in this case, the radius of my figure changes with angle. So approach 1 is let's see if we can convert to xy. To convert to xy, I'm going to multiply both sides by r. So r times r is 2r sine theta. Now why did I do that? It's because I get an r squared here and an r sine theta here, which can directly be written in terms of x and y. Because r squared is x squared plus y squared, and r sine theta is just y. So I get this equation. I'm going to use completion of square here to write this as plus 1 equals 0 plus 1, which makes this y minus 1 squared equals 1. Now this is a circle which has a center at 0, 1 and radius 1. So I can plot this. Center at 0, 1 and a radius of 1, which means it just touches the origin. So this worked out nicely, although you can already notice that we had to do some tricks, some algebraic tricks about writing this as a square in order to view it as a circle. There's an alternate way, which is just directly. What I'm going to do is I'm going to plot 2 sine theta in xy axis for now, just to look at the values. So between 0 and 2 pi, it takes a maximum value of 2 and minimum value of negative 2. These points are pi over 2, pi, 3 pi over 2 and 2 pi. Now if I look at my rectangular coordinate system and compare it to my polar coordinate system, this corresponds to theta 0, this corresponds to 90 degrees, 180, 270 and then back to 2 pi. So what is this relation telling me? It tells me that this graph is how the value of r changes. So that when I start at 0, my radius is 0, which means I am at the origin. Now between 0 and pi over 2, my radius increases, or my distance from the origin increases and reaches a maximum of 2. So from here, I reach a maximum distance of 2. From pi over 2 to pi, it reduces and comes back to 0, which gives me the exact same shape that I have here. This part is not contributing because it's saying that the radius is negative, which is not possible. Sorry, not the radius, but the distance from origin is negative, so it doesn't really contribute anything at all. So it's just the first half here, which makes the r go from 0 to 2 and then back from 2 to 0, which gives me the exact same circle. So that's a direct way of plotting, just by analyzing the relationship. Let's do that for this example. R equals 2 plus 2 cosine theta. If you convert this into a rectangular, it's going to be very, very messy and not easily sketchable. So we're going to use our direct analysis. So what this says is r changes according to this relationship with theta. So I'm going to plot 2 plus 2 cosine theta first. And to plot 2 plus 2 cosine theta, you start with cosine theta, right? You twice it and then you add 2, which means that it is never negative, but it does become 0. its maximum value is going to be 4, then it's going to go to 0, and then increase and become 4 again. At what values? 2 pi, going to be 0 at pi, halfway here at 3 pi over 2, and halfway here at pi over 2, with this being 4, this mid value being around 2. So unlike the previous case, here it's always positive, so r is always positive, which means the entire part of this is going to generate my actual curve. So let's look at what that is. And the reason I'm plotting these points here on the x-axis is because they correspond to, in the polar axis system, this is what they correspond to, the quadrants. Oh, sorry, it's pi, 3 pi over 2. Alright, so let's see. When theta is 0, my r is 4. So I am 4 distance from the origin, right? That is 4. Then what happens? As theta changes from 0 to pi over 2, my radius decreases from 4 to 2. Right? So it doesn't become 0, but it becomes smaller and gets somewhere here. So it reduces and becomes 2. Then between pi over 2 and pi, it keeps reducing, but this time it actually reduces to 0. So which means it curves back and comes back to 0. Now between pi and pi over 2, it begins to increase again to 2. So it's going to be symmetric. So exact same height over here, it increases. And then from pi over 2 to 2 pi, it increases further. This should be symmetric to get back to 4. So that is the graph. And this is a shape. It's supposed to be heart shape. Doesn't look like it in my drawing, but it has a name. It's called a cardioid. Okay. So if you are to draw this graph by analyzing, just as we did, that's what it looks like. Now just to give you an idea of how bad it can get, let's try to find the equation. If we try to find the equation, multiplying by r gives me that. Again, the same trick. This is x squared plus y squared, which is 2r plus 2. This is x. X squared plus y squared minus 2x is 2r. The reason I'm doing that is because if I plug r as square root of x squared plus y squared, that's going to be complicated. So instead I'm going to square both sides here. And when I square both sides, I get x squared plus y squared minus 2x whole square equals 4r squared. So the rectangular equation for this particular graph is that, which just by looking at it, you cannot tell what the shape is. So it's going to be way more complicated to plot this than it is to plot r plus 2 cosine theta by analyzing the relationship between r and theta. So this is an important tool later on in calculus where you look at functions and you're trying to find areas and volumes. Some functions, because of their symmetry, when they are plotted or converted to polar form, are much easier to analyze and much easier to study. And that's why it's an important tool. That's the end of this video. Next video, again, we're going to look at some more examples. Examples, and then also some ways of utilizing symmetry arguments when you are making these graphs.